Welcome again. I am Dr. Agbaoye Ridwan Olamide. We'll be taking week 2 of our PHY 314 class. Here we'll be talking about approximations and errors in numerical computation. That will take us through Unit 1 and Unit 2. In Unit 1, we'll start with approximate numbers, significant digits, rounding off, arithmetic precision, accuracy of measurement, errors, rounding errors, inherent errors, truncation errors, absolute errors, relative errors, and percentage error. Exact and approximate numbers. Of course, we all know about numbers, and we know that numbers can either be exact or approximate. But before now, we do not understand the numerical perspective of exact and approximate numbers. As it is, exact numbers are numbers as they are. Let's say, for example, I have 1 over 2. Of course, we know that's a fraction. That gives us 0.5. That's the exact value of 1 over 2. That is easy. It has no complexity. And if we want to store this, it's easy to store. We do not need too many computer space to store this number. But on the other hand, if I take 1 over 3, for example, and I punch that on my calculator, I would have 0.3333, and 3 keeps repeating. When do we terminate this number? And if we terminate this number, how does it affect our computation? So exact number is the numbers as they are, irrespective of how long they may seem, or irrespective of how repetitive they may look like. But in all of our computation, or in most of our computation, we cannot work with numbers as they are. Of course, perfectly we can work with exact numbers that are not so long. What happens when we have a very long numbers, like 1 over 3? Then we have a large complexity, because it's difficult for us to store this number, all of this number. That brings us to the idea of approximate number. We would like to approximate this large number such that the complexity is reduced, such that it is easy for us to save, but we'll be losing some precision. So that gives us an idea of what an exact number is and what an approximate number is. Then we can look at how do we approximate numbers. We can approximate numbers by first learning about significant digits. How do we know about significant digits? Here we have some example. In the first number here, I have 0.00123. Here, this we have only number 1, 2, 3 that are of significance. The first 2 zeros before 1 is not significant. And in numbers like this, the most significant is 1, and the less significant is 3. That is because we have a 0.00123. On the other hand, I have 14560000. The most significant, according to the rules as shown in your course material, is 1, and the less significant in this case is 6. 0000 are not significant. But in the third case, where we have 235.34200, 235.34200, the most significance is 2 and the least significance is 0. This is according to the laws as stated in the course material. Then we go to round off and precision. How do we round off number to a specific significant figure? The first number here we are to round up to 5 significant figures. So all we do is to first check how many of these numbers are significant. As it is, 3.142857143. All of them are significant. Then we count the first 5 significant figures, and that is 3.1428. The rule implies that every number after the nth significant figure needs to be truncated. It means we truncate 57143 after taking the 5 significant figures, which is 3.1428. Then rule number 2 is such that if the number after 8 is greater than or equal to 5, then we can add 1 to the number that precedes it. And the third rule states that if the number that precedes it is an even number, we do nothing. We do not add anything. But if the number that precedes it is an odd number, then we add 1 to it. So as it is, the number after 8 is 5. But 8 is an even number. Therefore, we do nothing. If we are to round off 3.142857143 to 5 significant figures, then we have 3.1428, and that is in 5 significant figures. For the second example, we have 6.324,31925. If we are to round to 5 significant figure, we take 6.3243 and we truncate 1925. And 1, which is the number that follows 3, is less than 5. Therefore, we add nothing to 3. So we have 6.3243. Therefore, on the other hand, if we are to round to 5 significant figures, 1.4123519, we count the first 5 significant digits, which is 1.4123. The next number is 5, and the number that precedes 5 is odd. So what we do is to add 1 to 3, and that gives us 1.4124, and that is to 5 significant figures. So what is the precision of this rounding off? The precision is accurate to the nth significant figure. So as it is in this case, this rounding off is accurate to the 5th significant figures. Then that takes us to arithmetic precision. Of course, precision is defined by the number of digits we have. When we have an exact number, of course we have a precise number. But when we begin to round an exact number so that we have a number that is storable, then the precision reduced. Therefore, the more numbers we have, the better the precision. That takes us to error. We have different types of errors as mentioned in our course material. And one of the errors we'll look at is the rounding off error. We just explained what rounding off is. When we round off, we truncate the number after the nth significant figure. So this is due to the truncation of digits. Then the rounding off error is reduced by increasing the number of significant digits, like we explained earlier. The next error we'll talk about is inherent error. Inherent errors are, in short or in simple terms, errors you inherited from a previous calculation. For example, if I am to multiply 1 over 3 by 2, and I took my 1 over 3 to be 0.33, it means I have truncated the remaining 3's. If I multiply it by 2, I have 0.66. It means I have carried over the errors I have from the first calculation into the second calculation. Therefore, I have some inherent error in my calculations. Another method or another ways inherent errors occur is from our measuring devices. Maybe one of our measuring device have some error values. It was used to carry out a measurement, and after the measurement, we use the values to estimate a particular parameter. It means that we have carried over some errors from measurements before calculation. So that is what inherent error is. And the third one we'll look at is truncation error. For example, you have a series, a Taylor series, for example, like what is shown on the Taylor series equation that is shown here. And I have the first order, the second order, the third order, and the fourth order. If I decide to truncate this to the second order, it means I have been losing some information in the third order and the fourth order. The errors that come out of this is referred to as truncation error. So truncation error basically is errors we got when we truncate series. It might be different series. It might not be Taylor series. But whenever there is a series and we truncate this series, we are bound to commit truncation error. Then we move to absolute error. Absolute error is the difference between the measured value and the actual value. For example, I may erroneously measure the mass of a ball to be 10.256 instead of 10.300. The absolute error here is 10.300 minus 10.256. And that gives me 0.044. That is the absolute error here. Relative error, like it is stated, it is actual value minus measured value divided by actual value, while percentage error is relative error multiplied by 100 over 1. And according to this little example, the relative error is 0.00427, while the percentage error is 0.427%. That takes us to Unit 2. In Unit 2, we'll look at linear graph, linearization, curve fitting, method of least squares, method of group averages. Linear graph. The relationship between two variables can be expressed in terms of a graph. And this will be governed by the equation of a straight line, y equals to mx plus c, where c is the intercept, m is the gradient or slope. We can consider a mathematical expression and look at the relationship between two variables in terms of the linear equation y equals to mx plus c. Therefore, plotting the linear relationship between the two variables in a linear graph or a straight line graph. In that case, consider the expression y equals to a exponential x. In this case, to express this equation in form of a linear equation, we can take the ln of both sides, and we'll have ln y equals to ln a exponential x. And if we express that further, we'll have ln y equals to ln a plus ln exponential x. And that ends up in ln y equals to ln a plus x. If we rearrange that, we have ln y equals to x plus ln a. And when we compare that with the equation of a straight line, the gradient or slope of the straight line graph is 1, which is the coefficient of x, and the intercept c is equal to log a. So that is how we express mathematical expression as the relationship between two variables governed by the equation of a straight line, as it could be plotted in a linear graph. An example of that is what we have in our course material a table of U and V, and we are to calculate the focal length. Of course, we know that the expression of our common optic expression, 1 over U plus 1 over V equals to 1 over F, come to the rescue here. And we are to plot the inverse of V against the inverse of U. Therefore, if we rewrite our equation, 1 over V equals to 1 over F minus 1 over U, it becomes the inverse of V minus the inverse of U plus the inverse of F. Therefore, comparing this with our equation of a straight line, our gradient M will be equal to minus 1. And our intercept will be the inverse of our focal length. It means the fact that our gradient is equal to minus 1, it means we'll have a negative slope graph. And the point where our intercept hits the vertical axis is the inverse of our focal point. Therefore, we can use that to calculate the focal length. Then we move to method of least square and group averages. Of course, least square method starts from the error from the drawn line of best fits and the exact point that was recorded in an experiment. And that can be expressed as S equals to the summation from I to N, yi minus mxi plus c. If we look at the extremers in this case, that is the partial differential of x with respect to m and the partial differential of s with respect to c, which is equal to 0. If we express this expression and we simplify it by taking the summation of the individual term, then if we are able to express it in terms of the mean of the individual values by dividing both sides by n, that will take us to a gradient or a slope m equals to the average of xi minus the average of xi multiplied by the average of yi divided by the square divided by x square I average minus xi average square. And with that, we can look at the equation of a straight line. The mean of y is equals to the mean of x multiplied by m plus c. The other way we can look at this is method of group averages. And what this does is to split the data into two. And when it does that, it takes the first part and it adds it to the second part. Let's say, for example, we splitted our data of data point n into two. And we call the first part L, the second part n minus L. We have similar expression. But in this case, for L, the expression that is sum over L and the expression that is sum over n minus L. We can express the averages in terms of L and in terms of n minus L, just like we did in the case of method of least square. Therefore, the gradient here, or the slope, is given as the average of y1 minus the average of y2 divided by the average of x1 minus the average of x2. And with that, we can consider our equation of a straight line. The average of y equals to gradient m times the average of x plus c. So that takes us to one of the examples we have in our course material. Here we have the values for length L and time t. Of course, we know that the relationship between the period and acceleration to gravity is t equals to 2 pi squared root of L over g. Then to solve this problem, we can take the log of both sides. We have log t equals to log 2 pi over square root of g plus log root L. And if we split this using the law of logarithm, we have log t equals to log 2 pi over square root of g plus log L raised to power half, and that becomes half log L. And if I decide to rearrange this, I would have log t equals to half log L plus log 2 pi divided by square root of g. With this, I have the variables of interest, log t, log L, and so on. But capital letter T is not given in the table, so it means we have to calculate the period for 50 oscillation. And like we know, period is small letter t divided by 50. So what we do is to create another column for period capital letter T. That will be 71 over 50, 69 over 50, and so on. Then we express log L, we express log T, we express log L times log T, and we express log L times log L. So with this, we can calculate the gradient and calculate the intercepts from our mean of y minus m times mean of x. And with that, we calculate our acceleration due to gravity, which is the intercepts, which can be gotten from our intercepts. And from that, we'll get our g equal to 2 pi divided by the antilog of c all square. We can do the same thing using method of grouped averages. What we do is to split the data into two. We have group 1, we have group 2. Then we express the period for each groups, and we also express the mean of log t1, log t2, log L1, log L2. Then we express the slope m, which is equal to log t1 minus log t2, divided by log L1 minus log L2. Then we can find the intercepts from the mean of y minus m times mean of x, and with that we can calculate our acceleration due to gravity. So this takes care of our week 2. Please go through the notes. We'll have time to discuss this in our 1-hour live session. Thank you and have a wonderful day.